Have you ever stared at a simple spiral pattern, only to look away and feel like the world is melting and swirling around you? It's a wild sensation, right? But it's not magic. It's your own brain playing tricks on you. Today, we read diving deep into the deceptive dance of light and shadow to uncover why our eyes and brains can be so easily fooled by optical illusions. It's a journey into the very wiring of our perception, and trust me, you'll never look at a simple pattern the same way again. So let's start with that spinning spiral. This classic illusion is a powerful example of the motion after effect. When you stare at the center of a spiral rotating in one direction for, say, 30 seconds, you're essentially fatiguing a specific set of neurons in your visual cortex. These neurons are specialized to detect motion in that particular direction. Think of them like tiny motion detectors, all firing away, telling your brain, hey, things are spinning inwards. But here's the clever part. When you suddenly look away at a static object, like the back of your hand or a wall, those fatigued neurons take a break. They temporarily stop firing. Meanwhile, the neurons responsible for detecting motion in the opposite direction which we're resting this whole time are now relatively more active. Your brain interprets this imbalance of signals as actual movement in the opposite direction. So even though the wall is perfectly still, your brain screams, it's expanding outwards. It's a fascinating glitch in our visual processing, revealing just how much of what we see is an interpretation, not a direct recording. It's your brain trying to recalibrate, creating a phantom motion that feels incredibly real. Now let's move from motion to patterns. Have you ever seen a picture of two finely striped patterns overlapping, and suddenly you see these weird, wavy, larger patterns that weren't there before? That's called the Müller effect. It's a perfect example of how our visual system can create something from nothing. The word Müller comes from a type of textile, originally silk, that has a rippled, watered appearance. The effect happens when two similar repetitive patterns like grids of lines, dots, or even the mesh of a screen door are superimposed and slightly misaligned. Your eyes and brain try to make sense of this visual chaos. Because the individual lines are so fine and close together, they can fall below the resolution limit of your eyes or a digital screen. Instead of seeing two distinct sets of tiny lines, your brain averages things out. It perceives the areas where the lines constructively interfere, where black lines overlap and create a darker band, and areas where they destructively interfere, creating lighter bands. This interference creates a brand new, larger, super pattern that seems to shimmer and shift as you move your head or as the image moves. You see it everywhere once you start looking. On television screens when someone wears a finely striped shirt, in photos of fences, or even when two window screens overlap. It's not an illusion in your head, but a physical phenomenon of wave interference that our visual system interprets in a peculiar and dynamic way. These static lines create a vibrant, moving illusion simply by interacting with each other. This leads us to a fundamental principle of our perception: perceptual constancy. Our brain is a master of stability. Think about it. As you walk towards a friend, their image on your retina gets larger and larger. But do you perceive your friend as physically growing in size? Of course not. You know they are staying the same size. They're just getting closer. This is size constancy in action. Similarly, if you see a white piece of paper in a dimly lit room, it reflects very little light, yet you still perceive it as white. This is color constancy. Your brain automatically adjusts for changes in lighting, distance, and angle to maintain a stable and predictable world. It's an incredibly useful survival mechanism. Imagine how chaotic the world would be if we perceived objects as constantly changing size, shape, and color every time we moved our head. But this powerful drive for constancy is also a key reason we fall for optical illusions. Our brain makes assumptions. It uses context clues, past experiences, and built-in rules to interpret incoming sensory data. Illusions are specifically designed to exploit these assumptions. Take the famous Ames room illusion. It's a distorted room that, when viewed from a specific peephole, looks like a normal rectangular room. But it's actually a trapezoid. One corner is much farther away than the other. When two people stand in the far and near corners, one appears gigantic while the other looks tiny. Why? Because your brain clings to the assumption that the room is rectangular. It overrides the visual evidence that the people are the same size. It concludes, well, the room is normal, so that person ** must * be a giant. The brain chooses to believe its assumption about the room's shape over the reality of the person's size. It's a tug of war between raw visual data and your brain's powerful interpretation engine, and the interpretation engine almost always wins. Let's explore this with another classic, the checker shadow illusion. You've probably seen it. It's a checkerboard with a green cylinder casting a shadow over some of the squares. There are two squares, labeled A and B. Square A is in the light and looks dark gray. Square B is in the shadow and looks light gray. The illusion asks, which square is darker? Intuitively, everyone says A, but if you isolate the two squares, you discover they are the exact same shade of gray. Your mind is blown. So, what's happening? Your brain is performing its constancy magic again. It sees the shadow cast by the cylinder and says, aha. Square B is in a shadow. An object in shadow reflects less light to the eye. For it to appear this bright while being in a shadow, it must be a very light color in reality. So your brain automatically brightens square B in your perception. It's trying to show you the true color of the square, compensating for the lighting conditions. It's not trying to trick you. It's trying to be helpful by creating a stable representation of the world. The illusionist just cleverly hijacked this helpful feature to create a paradox. It's a testament to how much of our vision is an unconscious, intelligent process of inference and correction. These illusions, from the motion after effect to the Müller patterns and the checker shadow, are more than just fun party tricks. They are windows into the workings of our own minds. They demonstrate that perception is not a passive process of receiving information, like a camera. It's an active, constructive process. Your brain is constantly building a model of the world based on incomplete and often ambiguous information from your senses. It fills in the gaps, makes educated guesses, and prioritizes stability over literal accuracy. So the next time you see an optical illusion, don't just be amazed by the trick. Be amazed by the incredible, complex, and sometimes fallible machinery inside your own head that's making it happen. You're not just seeing an illusion. You're getting a glimpse of your own brain in action, dancing between light, shadow, and assumption. Thank you so much for joining me on this journey into the mind's eye. If you enjoyed unraveling the secrets of perception, please hit that like button and subscribe for more deep dives into the amazing world of science. Let me know in the comments which optical illusion fools you every single time. See you in the next video.